Hi, hi. All right, take one. Hopefully, we can keep it at take one so I don't get checked out doing math problems on Thanksgiving. Wowzers. Okay. All right, so today, 6 questions. I want to go over 15, 16, 17, 19, 27, and 28. All right, so 15. A set of numbers is shown below. Okay, so this question, to do it fast, you just got to remember certain things, okay? Irrational numbers. Famous irrational numbers. Wait, radical 2, radical 3, radical 5, pi, and then in high school you'll see e a lot more, okay? E and maybe radical 5, okay? But just remember that these are irrational, okay? Also, um, if you want to see which ones, why the other ones are not, the way they teach it here in this grade level, we say, oh, fraction with a repeating decimal, that's rational. So A, this is rational. B, this is rational because the 3 is repeating. So the answer here is going to be C, right? And then D is rational because the decimal terminates, right? So this is 2.5. Okay? All right, 16. Which expression is equivalent to 3 to the power 5? So this is testing your laws of exponents knowledge, okay? So you have to check each of these, do the laws of exponents and possibly some PEMDAS to find out which one is 3 to the 5th. Okay, so for A, PEMDAS doing this, you have to do the numerator. So 3 to the 6 times 3 to the 4, so that means you are using the product rule. Same bases, both 3, so you just got to add the exponents. So 6 plus 4 is 10, so the top is 3 to the 10. So this is equal to 3 to the 10 over 3 squared, and now you're dividing two numbers with the same base, so you use the quotient rule. So that means you keep the same base and you subtract the exponents. 10 minus 2 is 3 to the 8. 3 to the 8 is clearly not 3 to the 5, so it can't be A. B, you have to use power rule. So here, 3 to the power of 2 raised to the power of 2, that means you just multiply the powers. So 2 times 2 is 4, so this is the same thing as saying 3 to the 4. 3 to the 4 times 3, that's using product rule again. So 3 to the 4 times 3 to the, what power is here when they don't include it? It's a invisible 1. So then that's the same thing as saying 3 to the 4 times 3 to the 1. So then 3, which is the same if you want to write the work, 3 to the 4 plus 1, which is equal to 3 to the 5. So this is the answer, okay? But let's just go to the other ones just to be safe. Power rule again. 2 times 3, that's 6. That's going to be 3 to the power of 6. Okay, and then this one you use, pause, you think about it. Okay, this is quotient rule. 3 to the 15 minus, so 3 to the 15 minus 3, which is going to be 3 to the 12. Okay, so it's B. Next. 17, more geometry stuff. Okay, so rectangle JKLM is graphed on a coordinate, Okay, so the key main word is this, translation. Okay, so translation is a fancy way of saying moving a shape, okay? So when you move a shape on the plane, um, think about what's happening, right? Like, so here you're moving it 5 units to the right and then 2 units up. So then this thing is going to move. Every single point is moving 5 units this way and then up 2 units. Okay. So what does that mean about the actual sides and all its properties? It's still intact, right? Because if I'm moving it, it's just gonna look something like this. This is a sketch. It's not being precise. On your free time as an exercise, you should map these by moving it 5 right and then 2 up, or yeah, you can add and subtract plus or minus something on the coordinates for faster. Okay, but it's gonna end up somewhere here. Okay, so then here you have to find out what's true about the line segments of rectangle J prime, K prime, L prime, L M prime. Oh, let me also say something. When you're doing these things are called transformations, right? When you're transforming shape in math and geometry, what they say is like, more formally, a transformation is a specific kind of function, okay, that maps the points in your space to some other points, right? So here when you map like let's say J under some transformation, here's the translation. It's gonna move. They use this thing called J prime. Okay, this looks like an exponent. It is not an exponent. Okay, the way that you say it is J prime. Okay, and this is supposed to indicate that you transformed it somehow. Or another fancy word. That's a fancy word of saying map or there's a function. Okay, all right. Get used to all of these terms. It's good for your higher math. Okay, so another symbol that you should know. It says here, this thing, the double lines, this is parallel, okay? And that's pretty intuitive because parallel lines, they never cross, and it looks like two L's like that, right? and those are not crossing, okay? So then think about this translation here. It says J prime to K prime, so that means that J prime is going to end up somewhere here, right? K prime is going to be here, right? And then L prime is going to be somewhere here, and M prime is going to be somewhere here. This is very sloppy, so you have to really use my audio, okay? So think about it. So J prime, K prime, so this line, or yeah, sometimes they use this to represent lines, sometimes they use it to represent line segments, okay? But I don't think that's important for this example. So J prime, K prime, is it parallel to J prime, M prime? No, right? Because J prime, K prime is this, and J prime, M prime is this. That is perpendicular, so that is the opposite of parallel, so it can't be this. J prime to K prime, is it parallel to L prime, M prime? Yes, and it's gonna be B. Okay, but let's just double check the other ones. K prime to L prime, and then so K prime to L prime is this. To J prime to K prime, that's also perpendicular. K prime to L prime, that's this piece, right? And to L prime to M prime, that's perpendicular, so no. So that's gonna be B. Okay, next. More geometry. Okay, great. So 19. So figure ABCD is shown on the coordinate plane below. Okay, the resulting image. Okay, so going back to the transformations, right? Image. This is related to functions, okay? So sometimes they call the output of like an input under some function, they call it the image. Okay, so for example, if I have an input x, right, and I put it into my function like this, like let's call this function f, then the output I said was f of x, right? So a fancy way of saying f of x, sometimes they call the image of x under function f, so under f, okay? So anyways, the resulting image, that's what it is, okay? Oh, okay. This is funny. So here in the test, they I'm not sure if they meant to say image, the mathematical image, or the picture, but I'm just gonna assume the picture here. Okay, so if that's the case, then this is not that important for now, but this is very important for future, okay? Will be figure A prime, B prime, C prime, D prime. Okay, so the important word for this example is dilated, okay? Dilation, okay? So think about how you remember this. This means like shrinking or scaling, okay? So it's either like stretching the picture or shrinking it, okay? And the way you remember this is, think about this phrase. What does it mean for your pupils to dilate, okay? The pupils to dilate, okay? It's getting bigger, right? Or something like that. But here, the dilation could also refer to something smaller. Okay, so what will be the coordinates of vertex A prime? Okay, so here, okay, so just think of, okay, so in math, dilations also, in a coordinate plane, there will be some reference point that you are dilating with respect to. So here, it's saying that the figure will be dilated by a scale factor of 2 with the center of the dilation. This is your reference point, okay? The reference point is at the origin, okay? So the key idea is that whenever you dilate an image with respect to this reference point, so this line, right, from the origin to A, the image of A, so the A prime, it's gonna end up somewhere on that line segment that passes to the point and the reference point, okay? So A prime is gonna end up anywhere on that green line, okay, and then B, we'll say B is here, right? And then the reference point again, so that means that the image of B under a dilation is going to end up somewhere on the red line, and then you could do the same thing for D, right, and so forth, okay? So what does that tell you? Well, when you're dilating by a scale factor of 2, okay, this is also very important, scale factor of 2, sometimes they call the scale factor K. When you have a scale factor that's, let me call it K, right? When it's bigger than 1, this thing means you are expanding, okay? So you're making the picture bigger, okay? And it's still going to keep its parts in proportion, but yeah. If K is less than 1, this is a shrink, okay? And if K is equal to 1, then nothing happens, okay? So this is like neutral, okay? So, yeah, so think about it. So that means that you have this A, right? And you're expanding it. So that means that the A prime is going to end up further away from the origin. It's going to end up somewhere here, okay? So here, what will the coordinates of vertex A prime be? It's got to be somewhere deeper there, right? In quadrant 2. So if you look at the choices, the only ones that it could be is D or possibly this, okay? Let me see, what else do you need for this? Yeah, so also another thing, when you're dilating, right? I said that the corresponding parts are in proportion. So that means if you look here, at this line segment, right? So from the origin 0, comma 0 to A, right? And A is what is that? Negative 3, comma 4. There's a distance here, right? There's a right triangle. Okay? Um, there's a right triangle, and that distance is the hypotenuse, right? And if you do the math, you have to think about this a bit, right? But this is going to be 5, okay? Because negative 3 squared plus 4 squared, and then square root that, okay? So, um, yeah, that's going to be 5. Yeah, 5. And then under this, when you uh, multiply it by that dilation factor k, the scale factor k. So k is equal to 2, right? So then that means that after the dilation, this thing is going to be 5 times 2. It's going to be scaled. So that means that the new distance is going to be 10. Okay? So then that means that it's going to end up somewhere here. And then now you got to find the point which gives you that line segment 10. So from these points, if you do this math, you use the Pythagorean theorem on this, that's going to be negative 6 squared plus 8 squared, right? And you take the square root of this. This is going to be square root of 100, which is equal to 10. It's going to be this choice, okay? Yeah. And then you can try the other ones, and it's not going to be it, right? But yeah, I wonder how they teach this in 8th grade. I don't remember learning this in 8th grade specifically like this, but there might be easier ways. But this is the formal way of doing it, okay? So one more time, in the dilation, when you dilate, right, when you dilate a figure, the parts, the corresponding parts after the dilation will be in proportion. So you're scaling every side by the same amount and stuff, okay? So yeah, that's the main thing. Okay, so yeah, 27, more geometry. Okay, a diagram of a right cone. What is the volume? So volume, once again, it's a space inside a three-dimensional object. So here, okay, so use the reference sheet. They should have this. So the volume of a right cone, it's 1/3 pi r squared h, okay? A good way of remembering this is, okay, think about in a right cone, right? If I trap this inside a right cylinder like this, right? it looks like this is about like 1/3 of the cylinder, okay? And this thing here, this is the volume of a right cylinder. So that's a good way of remembering it, right? But all you got to do is just use this formula. So 1/3 pi r squared h, and you need to know which one is the radius and which one is the height. The height is clear. The height is 8, right? So that's going to be 8. And then r, the radius is, it's like it's the distance from the center of the circle right here to the point on the circle. You just say half the diameter. So if this diameter is 6, so then the radius would be, half of that is 3. So it's going to be 3 squared, right? And then you times pi, and then I'm going to divide all of that by 3. That's the same thing as multiplying by 1/3. Okay, so when you do this math, you're going to get 72 pi over 3, which is the same thing as saying 24 pi. Okay, and this is nice because they said you could leave your answer in terms of pi. Okay, great. And then one more time, 28, a transformation maps triangle ABC to A prime B prime, okay, is similar but not congruent. So which transformation occurred? Okay, so if similar but not congruent, congruent means the side lengths are all equal, okay? And there's more to and like the angles are equal too, right? But similar but not congruent means that this thing, this transformation is not a rigid motion. This is the fancy way of saying this, but just look it up. A rigid motion is just a distance preserving map, okay? So some rigid motions that you have to remember, rotation, because when you rotate an object, that's still going to preserve the side lengths, right? And the overall shape, right? So, and thus the congruency, okay? A reflection, when you reflect, it's like you're flipping, you're still going to preserve the side lengths and the original shape. A dilation, as we just discussed in the previous problems, that is not, it's going to change the shape, so that's not a rigid motion, okay? And a translation, we know we're just moving the shape, so the whole shape is still going to be preserved. So it's going to be C, okay? That is it, okay? That 15 minutes. Hopefully this thing is good. I don't want to do a take two, but yeah, happy Thanksgiving. And yeah, I'm very, very grateful for the memories we had, right? So study hard and be good, okay? See you.